welcome to my talk today. I'm going to talk to you about the power of tracking invisible geoinformatics and social human behavior. Thank you very much for the great introduction. And I'm going to make a smaller introduction about myself. As they already told you, I'm a passionate software developer and a project manager, and I have been involved in private and public sectors, helping developing products in Latin America and Europe as well. Currently, I'm pursuing my PhD, my doctorate in geoinformatics in Germany, and doing this process after doing my master in geospatial technologies and my engineering program in cadastral and geodesy engineering in Colombia. I got very much interested in integrating spatial cognition and computer science because we have this impression that spatial science, every time that you hear about something being spatial of geoinformatics or geospatial, is related to maps. But no, I want to show you today that the spatial science goes beyond geographic maps. Imagine the scene that you're walking in a museum and you go to a point to another. And then you are maybe alone or with someone else, but you are moving through the space. When you do that, sensors can help us to detect to what are you looking at, to where are you walking, how is your body orientation, your head orientation, and we can also see the path that you have been walking in that space. That is what we call the physically occupied space. But the way that you move can also tell us something about socially occupied spaces. Socially occupied spaces are defined as those invisible spaces that are between you and the others. When you are walking, you know that there is a space right over in front of you that you cannot surpass, that you are not going to invade, right? So how can we help sensors to depict these spaces? In cases, for example, when you're looking at an exhibition, very rarely someone is going to cross in front of you while you're looking at a picture. And if you're looking to something, you most likely are going to avoid blocking someone else's way. But not necessarily you need to have an object in front of you. You can also construct these socially occupied spaces with others. So you can be with several people and you are going to close this interaction. And you're going to have a body orientation, you're going to have a head orientation, and so on and so forth. So why would we like to track these kind of behaviors? For what do we need those? For example, they have been proven to be useful to improve architectural and exhibitions designs. When you are in a museum or when you are in a store or in another place, we need to find ways to know how to optimize the spaces. If there is a very cramped space, we need to do something to release that crampiness, that hotspot. But when we are in an empty space, how can we improve the navigation towards that space? Also, we can use this information about how your body is oriented or what are you looking at to offer better services in the stores. When we are having this stands with a lot of staff, you want to know how much distance are going to be with that. Or when we have these islands with products, we want to see how your body is behaving around that and how your body and others' bodies also have access to this information. Also, we want to analyze the behavior during interactions. We knowing who is in the conversation, how many people, and how are you arranged. We can see who is the leader, who maybe is the shy person, which people are leaving the conversation, or which people are arriving to this conversation. Also, when we start understanding the factors that are involved in human interactions, we can create appropriate social behaviors for robots. So we can develop several algorithms to make the behavior of robots towards humans more natural. If we have these, then how can we detect human behavior automatically? From research, we have been seeing that before detecting human behavior or analyzing human behavior in social spaces have been done manually. So people take notes, take timestamps, they annotate how is your body orientation. But nowadays we have a lot of technology and the computational power to make these kind of things automatic. And if we want to do that, what then should we track? Imagine that you have, again, this scene in which you are in different spaces. Here we have the individual position, and we know which are the coordinates of your body in that space. We also know the trajectories and in which point you are going to create a group. You are going to have an individual and a group trajectory. And then when you have enough focus of attention with people or to an exhibition, we will know all these factors that we already mentioned. And that is something that comes from computer science and something that is called social signals. Social signals are all these characteristical behaviors of humans that are very interested to model for future algorithms. We are going to have into account the groups theory, that is the interaction, and also the people that participate in this interaction. We are going to have variables such as path and environment that have the distance, this proxemics theory, how far, how close are you to each people, to each one of the individuals in the space, how are you arranged, if you are seated or if you are standing, the face and eyes behavior, because we want to see your gaze to what are you pointing at, and your focus of attention, for how long are you paying attention to something. The gesture and posture is likely related to the body orientation, if your shoulders are to somewhere else and your face is pointing somewhere else as well. How can we extract this data? We already talked that we can do it manually, but we don't want any manual observations. We want a simple design and something simple to set up in the environment. We want something unobtrusive, because if people know that you are following them, most likely they are going to change their behavior. And also we want to keep our identity safe. We have currently these privacy concerns and we want to keep them as low as possible. Our approach, the approach that I'm doing in my research, is to use skeleton data. So we remember that we at some point have drawn this kind of skeletons with the limbs and the main part of your body and so on. We can make it very complicated. We have these small points like you can see in the draw here in the skeleton, and those we are going to be calling joints. Each one of the joints is going to depict one of the parts of your body. So for example, here is the head, here is the clavicle, the shoulder, the elbows, and so on. And if we use this along with a sensor in an exhibition, for example, we are going to be able to extract the skeleton without knowing who was there, and we're going to see to what are they paying attention most likely and which area are they occupying. But which technology will be the most useful for doing this? There are many cameras that can do this. We have several technologies such as infrared, we can use Bluetooth, we can use Wi-Fi, and so on and so forth. But today we're going to focus on two main technologies. We are going to focus on optical and vision, that is from computer vision more than RGB cameras, and we're going to have a look at the OpenPose library that you can simply use with one webcam, and that's all. And also we're going to have a look at a more complicated approach, that is a stereo deep camera, and we're going to have a look at the Z2i camera. So first of all, we're going to talk about OpenPose. OpenPose, as I said before, is going to use vision. So it's going to check the image that you're going to receive. You can have it as a feed in a picture, or you can have it as a feed in a video. The accuracy will depend a lot on how is the resolution of the camera. So it's like resolution constrained. The cost can be medium to high because different models can be more or less expensive. The complexity can be high because of the configuration and the technological requirements that it's going to have. And the scalability will be low. By scalability, we mean that how likely are we going to reproduce this in the environment, and how likely or how easy is to implement this for a project. In this scenario that we're depicting in the right side of the slide, you will see that there is a camera 1, 2, 3 to 5. And from all those poses that we have here, all the perspectives that we got from the camera, we have the poses, the 3D poses that we are able to extract with computer vision techniques. So you can depict that they are shaking hands, that she's sticking her head, that someone is playing something, an instrument or something. And that is why we are very interested in processing this data. In here, you can see the animation in which this can be live. If you have the camera and you have the algorithm, you're going to be able to depict how people are moving around. So how can we install and configure this camera? We're going to have a look at the library setup and the folder and how this depicted this model. So if you come with me here, let's close this. You are going to see here the open pose. And in open pose, you are going to have here the GitHub of the Perceptual Computing Lab. Here you will have everything that you need for this. And they're going to show you the contents and everything. But when you want to install it, you should go to the releases, and you're going to start the latest release. So in my case, because I'm in a Windows computer, I will have to extract this one, the recommended one, extract it, the files, and then when you extract the files, you're going to end up with this content. The first step that you should take in this is to go to models and run the path file. That's going to start the downloading all the models that you will need. OpenPose relies on the body model to extract body structures, but it can also be very detailed in the hands, that's all that kind of algorithm, and also in the face. So I can run it here, but you will see that it will go super fast because I already have all of this. But if we go to the slide, we will see here exactly the same content. And here you will see that is download the pose, and it will go iteratively the downloading everything: body, foot, face, and hand models. Once you do that, there are two main things. You can use the OpenCV by a manual installation, you may say, with CMake. You make everything there, and then you also have the option of the terminal. You only go to CMake and compile everything in a Python environment if you need to create or modify an algorithm to develop another technique of processing the RGB that you are receiving. So this is very, very specifically if you are going to develop something new. But if you only need the data and you are only interested in processing this data, you can do it by the terminal. And in the terminal, we are most likely going to use the main flags. If we come back here, you will see that we have here different sets of documentation in Markdown files. And when we go to the demo one, we are going to have a lot of information in which you are going to see each one of the requirements that it's going to have. But the most important one is going to be this terminal one, the main flags. So we're going to be able to check the face, the hand, which camera we're using, if you want to display something or not. So how do we implement this? We already know how to install it. It's an easy download from the GitHub repository, you easy install, and so on. So in here, as I already showed you, there is a documentation about the demo, and then we're going to go to the console to check how is this. So we are here in the OpenPost. You will see that this is exactly the folder that we have. We're going to have some examples here in the media. If you want to process photos, you don't need a camera for doing that. And also here we will see the different models that we download. So if we go here and we go to the bin, OpenPost demo, OpenPost demo exe, and then we're going to check in which camera. The only flag that you need at the moment is to open your camera. So let's check in which camera can we open this. So right now you can see two cameras because we are using the stereo vision camera, and later we can talk about it. But because we have two feet and two bodies, here you can see that it detects two bodies, but you can see how I move and everything, how many frames per second, and so on and so forth. But for example, if I didn't want to show you my background, we go to disable blending, and then you are not able to see my background or anything. You are going to have the camera. But let's change camera so we can have one body. So looks like we select the ground camera. Maybe that's the one that you are looking at me right now. Perfect. Now we access another camera. So you can see here the body without the background and anything else. But if we want even some more detail, we can also add the face, and we can also add the hands. And here you can see how the hands moving. If I get a little bit closer to the camera here, or if I move my face, it's going to be depicting all the borders of my head. And if I move my eyebrows, it's also going to depict the eyebrows and how I move my mouth, how I open and close my hands as well. And that's by simply processing the information with the camera that you have at hand. If we want to check this data, for example, you want to process the joints that you have, you are going to import most likely this data into a JSON files. So we use the flag write JSON. We select a folder in which we're going to put this. We run the command again. We do some movements to get some data. And you can see here that we created our data folder. Each one of these is going to be one of the frames that we have at the moment. Let's format this so it's more human readable. And then you will see here that it's going to show us the open post version, the people arrangement here. There's going to be only one person and the poet's king poet. So here, let's do it like this. This is the coordinate X, the coordinate Y, and the level of confidence in which the algorithm has detected your joint. So if we return to here, here maybe you can see it better. We are going to have this 0 joint that is in the map. This is in the right side. You are going to see the map for the joints for the open post. So each joint has an identifier. And that identifier is going to correspond to the key in your list. So you're going to be very careful. Each key that you have here is going to show you that. But when you move here, every third one. So you're going to have the coordinate here, the X, then the coordinate Y, and then the level of confidence. And why the level of confidence? When you have the algorithm that is translated the post, you're going to have a pair candidates here. And then it's going to show you the level of probability, the confidence that it has of predicting that join. And you will see here that it tried to do it 4, and this is the one that had the highest level of confidence, and that is the one that the algorithm is going to return to you. So if we go here again to our code, we will see that we have a lot of files to process with that one. If we use the flag that we want the pair candidates, data, so we don't mess up with it. We need the pair candidates to have that level of confidence if you are interested in processing that or not, and run the algorithm, run the command in the console and have everything again. So if we move forward on the test, you already saw how we were moving around. But here, for example, I create a video for you when I'm moving farther away, and you can see my hips, you can see the legs, and you can see my hands moving around. And obviously, because this is something that is based on computer vision, it will have high resources consumption from your computer. So take into account that for some computers can go very fluid, or for others it will be slower. Now we go to the Z2I camera. And the Z2I camera is going to be a stereo depth camera. And a stereo vision is the same thing that works with how your eyes work. You're going to have a perspective from your right eye and another perspective from your left eye. This is going to be an accuracy like for millimetric accuracy to centimeter, but it's going to be based on the configuration of your camera. The range can be from 1 to 20 meters. And that's very useful because when you have this kind of things that you are using more depth information, you're going to have an additional coordinate that is the C coordinate that is going to tell you the distance. Whereas the disadvantage that we found in RGB cameras is can only be in a 2D space. So you are not going to be able to see from this data the exact location for all the objects. The cost can be medium to high. The complexity, of course, is going to be high. The scalability is medium because you don't need as much cameras to go through the extracting information that you need. But also there is a factor that you need to have into account, that is the light performance. You can have a weak performance if it is a low light, but if the light is bright, then you are going to have good results. So in here, if you are very carefully looking, here's on the L from left, are from right, and you will see that it's slightly different, the perspective. And when you use this data in stereo vision, it works that the difference between the distance from the left and the right image is going to tell you with another, of course, mathematical equations, how deep is the image, what is the difference in between the distance. Then you are going to have this kind of map that you can create in a mono scale. The further objects are going to be dark, and the closest are going to be blue, white. So the brightest the color, that means that is the closest to you. And if you have a look only to the right one, you're going to have that this perspective of deepness that you're going to have in the image. And this is going to be very helpful because, for example, someone is playing, you're going to be able to identify and to have the body's identification and the velocities and everything. And also you will have something that is more reliable regarding to the location and the distance of the people. In here, in the smallest one, you can see a point cloud depicting the scenery that you are having a look. So how we install and configure this? If we go to the camera setup, you need, again, to be careful with the requirements. You can do this in a Windows machine or in a Ubuntu machine. The processor needs to be a quad core at least, from 2.7 gigahertz or faster, a RAM of 8 gigabytes. The graphic driver should support CUDA. The graphics card preferably higher than a GTX 1060. And more important, and sometimes that happens a lot in labs, that a USB port 3.0 is necessary. A lot of cameras, don't worry if you don't have enough velocity in there. Then when you have the camera set up, then we can go to all the links that belongs to the set. So we already talked about these requirements, and you can go to the Stereolabs website, in which you will have the SDK download. You can download it for your required operating system, and while you are installing this, it's going to help you also to configure your CUDA, so it's going to be fine. Once you have finished everything and you completed the wizard and everything, then we can go to the different applications that this camera is going to install from you. So for example, if we go to diagnostic, it's going to tell us everything that is grown up with the camera. But if we go to Explorer, you are going to have here the left and the right camera, and it's going to tell you the frames. If we go to another one, that is the depth viewer. Whoops, we are using all the cameras. So let's do in that. In that case, in here, you're going to be in this part. That you're going to be having the point cloud, you're going to have the depth information, and then you're going to have also the RGB image. Good. There are two methods in which you can use this camera. You can do it manually, but you can install it manually by the script, the Python script that it comes in the SDK, and that is going to install all the dependencies and everything that you need. And you can do the same thing in Linux. Another thing that you can do if you want to avoid a console is to create an Anaconda environment and install the different requirements that it will need. So if you go to Anaconda, you create your environment, the most important package that you need to take into account is the one called PySet. Here it is. Once you install PySet, then it's going to install all the requirements that you will need. And you can see here, it's going to do the same for this. So how do we use it? If we go to the Stereo Labs documentation, you will see that you can create a C++ environment, a Python development, and so on and so forth. And you will have all the tutorials and everything. If you go to the GitHub repository as well, you're going to have all the examples and everything. So once we go to the body tracking, for example, here I have the set examples repository. You can see the body tracking, camera control, depth sensing, and so on and so forth. Because when you use this camera, it's also used in navigation for robots. So when you are traveling with a robot and you're trying to recreate all the point clouds from the scene and you want to recreate in 3D the room, you can use this kind of cameras as well. So in here, You will have already the code that you will need to process the data. So we have here the famous byte which you just mentioned. Some parts very important to have into account in the code is here the coordinate system. The camera can have 6 different coordinate systems. So according to your requirements and how you want the data and how are the navigating and the elements that in which you are using the camera, you should change this. Another very important parameter that you need to take into account is the body format pose, because you can have very complicated skeletons with 34 joints, or you can have simple ones that is from 18 joints in the case of the set camera. And once you can have here and you have configured your environment, of course, if we run this, and we have enough GPU, looks like, then you are going to see the body moving around. Okay, looks like it's too complicated with streaming working at the same time. So let's lower down a little bit the performance. And while this is processing here, you will see that it has the detail of the eyes and the ears, and you can see that this one doesn't have the face detection algorithm. This one is not going to have that one, doesn't have that model, and also the hands are going to be very simple. When you want to, for example, extract, as we did with the other one, you modify the code. And when you modify this code, you are going to have access to all these variables here that works as very similar to the open pose. You're going to have the pelvis, the navel, spine, the chest, and the neck. Then you're going to have the objects, key point 0, 0, 0, 1, 0, 2. But what does that mean? If we go here to the skeleton again in the slice, you're going to see that pelvis is going to correspond to this joint. That is going to be your joint key. That is going to be this first part. And then the coordinates, X, Y, and Z, because we're going to have the distance from the camera towards the camera. The origin of coordinates is always going to be the camera. That's why it's very important to have into account your coordinate system at the beginning. The test, we already did a test. But there is a video in which you are seeing the entire body moving from one side to another. So we have all this data and we have this technology. Which applications can we do with this? And one that I'm working right now is in detecting social groups. In my research, I'm very interested to see how people move into space and how they create social structures. How you, when you are with your friends, create your groups, in which shapes are going to be your groups. So this is skeleton. Data processing algorithms is completely developed in Python with a supervised algorithm. And then you're going to see here the process. We process the JSON files, then we create the data sets that we need from the environment or from the skeletons. We transform the coordinates, and with all the joints and the evaluation of everything, we can have what we have in the red side. And in the right side, you will see that here, I know that people were moving together in this place. And in Python, you can extract what is the left joint and which one is the right joint. So here you are going to have your left joint and your right joint. And you can draw a line to draw the shoulders line. And once you do that, for all the timestamps, you are going to see where the people were looking at. And when you have these joints, you can calculate the body orientation. And these arrows are showing the angle in which the body is moving. So we can see that people were looking in this direction, and then here are many, because that means that someone stopped there for a longer period of time. That's why there are a lot of points in there. And we can see that they are moving. And in here is very interesting. You will see that when we look or when we are placing our body in certain orientation, we have one point of inflection. So in this case, this person rotates from the right shoulder. And you can have all kinds of observations from this. And here we have the analysis of the information of all the how the orientation was calculated in the entire field of view. So for example, in the right side, you will see that they were looking always on the right side in a certain pattern. And the weak points from the camera will be very front, in the very close points, and also is going to be in the borders. With all this information, we can have a group detection algorithm. And with these group detection algorithms, now that we know the body orientation, the location, the trajectory, the timestamp, all this information, we can evaluate this information and check where are people paying attention, are they paying attention together, and how long are they paying this attention. So we analyze proximity, how far are one to another, and in proximities, there is a theory, you will see that there is a personal distance, a intimate distance, or a public distance. Then when we have these kind of characteristics, you are going to have that you can calculate the focus of attention. So how long these people are paying, how long is this field of view that you have to another elements. And when these elements intersect to each other, we can analyze that all the people, the ones that are intersecting their field of views, most likely are paying attention to the same thing and they are sharing a moment together. And when we run this algorithm in all the samples that we have, we accomplished and we saw that 90% of the cases we were able to identify to where people are paying attention and if they were a group or not at that point of time. With that information as well, we can draw the area in which they are interacting, so we can limit towards where they are going. Of course, there are some challenges. Social challenges include the cultural context because people in Japan don't behave exactly the same than in Europe, and Latin American people, we sometimes are their distance or personal distance are shorter or greater. There are privacy concerns because, of course, we are analyzing people's movement and so on and so forth. But also there are some bias in algorithms. Some algorithms are going to have into account the height, the weight, or they're going to be, as you may already know for computer vision, some skin color bias. Also, there are some technical challenges. For example, the computational power, as you saw during the presentation, if the camera requires a specific computational power, a graphics card power, then it's not going to have enough room if you have several tasks. Also, it's going to need to take care of the environmental factors because it can be some reflections in the environment. If everything is of the same color, then you are going to be merged with the environment and so on. Also, the setup configuration and placement is very hard in some cases. In a museum, you cannot place cameras everywhere that you want. And in some stores, you can also not do that because that's part of the environment, of the feeling of the environment. And you don't want people to be uncomfortable with the cameras. Nevertheless, all this information, all this data compilation, and all this analysis will help us a lot in the future. Because with this data, we can improve the services that we use, the places that we explore, and of course, the artificial agents that we're going to create in the future. So both analyzing this invisible space without going towards your privacy and towards going into more technological design, is going to help us a lot in the long run for these three aspects. Thank you very much for your attention. I hope you find it interesting. If you want to find me somewhere, Violeta's Dev, mostly everywhere. You can find me on Twitter, LinkedIn, on GitHub. And in the QR code, you will find my handles. And I open to your questions in Spanish or in English if you feel more comfortable. Thank you very much.